I'm not able to share the slides, so that's why I've requested you to come after 5 minutes. Okay, so now it is working. Okay, so now, uh, okay, so today we are still at unit 4 only, that is power flow control and real power scheduling. So under this, so we have completed lecture 4. Till lecture 4 we have completed, and then today we will be studying on the lecture 5, that is optimization. Okay, so earlier we have done real power scheduling, and then it says it's not that accurate one, right? So mathematical procedure we can follow this by optimization. Okay, so basically you know what is optimization. Okay, so optimization is basically you are trying to optimize the cost considering different constraint of a power system. Okay, so it means as far as possible you try to optimize and then make the cost of the energy cheap, or power system energy cheap, okay, as far as possible. Okay, but when you optimize you have to see different from different angle, which means different constraint. There are a lot of constraints. So we have studied in earlier, there are equality constraint and inequality constraint. So today we'll see how to carry out the optimization if there is only equality constraint, and if there are inequality constraint. Okay, two cases. If you are able to understand these two, then it will be very, okay, so it's simple. Okay, so but detail of optimization, so next semester we will have one full module to study on optimization. Okay, but here you have to be mindful that we are doing only the introduction to the optimization. Okay, but optimization basically how you will understand is roughly we can understand that. So considering different constraint in the power system, we are trying to optimize the cost, which means as far as possible you are trying to make the power key cost less or a cheap. Okay, so now we'll see that, okay, so how to carry out the optimization considering the two constraints. One is equality constraint and another one is inequality constraint. So this is the objective of today's lecture. That is, how does one solve a
Sir,
constraint? Pardon?
we can see the slide, sir.
Okay, you are not able to see that.
No, sir.
Okay, once more I'll try that. If it is not favoring, then I will call off. Okay. Okay, are you able to see?
Yes,
Yes,
sir.
Yes,
sir.
sir.
Okay, so today we will see the optimization on. Okay, so in this lecture, you will learn the following, which means how does one solve a constraint optimization problem, and with one example, okay, illustrative example. So with this, so we'll try to end the optimization. Okay, which means in detail about the optimization you will learn in the 7th semester. That means next semester you have one full module on optimization. So we learn detail, but here what we will do is we'll just see the two constraint of a power system and try to solve the problem. Okay, one is considering equality constraint, another one is inequality constraint, and then we'll try to see how to schedule the real power. Okay, okay, so first before we do this with the example, so first we have to know this constraint and unconstrained optimization. What is mean by constraint and unconstrained optimization? So when somebody talk about the unconstrained, first let's see unconstrained system. The its approach is to minimize the cost function. Okay, so which means our aim when you do our optimization, our aim is to as far as possible we try to make the energy cheap. Okay, but when you make the cost of the energy cheap, you have to see from different angle, which means there are a lot of constraint which we have to involve. Okay, so maintenance also there, then all costs has to involve, and then you have to find one final solution. That is, that solution is a call it as optimization. Okay, so which is to minimize the cost function to set the function derivatives to 0 and then solve the control and auxiliary variable from set of the resulting equation. Which means when we talk about the unconstrained system, we are trying to minimize the cost function. Okay, so in earlier example, we have learned cost function C equal to, considering a two system, we have seen that C equal to C1 plus C2. And then we have to minimize this C1 plus C2 considering different constraint in the power system. Okay, so that means what we have to do is set the derivative to 0 first and then solve for the control and auxiliary variable from the set of the resulting equation. Okay, so with example I will explain that and you will clearly understand this. Okay, then what you can do is, so first you have to do this and then you have to minimize this cost function and then you will make in the form of matrix and then finally you will get this solution. Okay, so we'll see that, and then solution is obtained by setting the partial derivatives of this function minimize ju with respect to every control variable u to the 0. Okay, so this one is just a step I am explaining. Okay, so then number of equation will be equal to number of control variables. So if there are 5 control variables, so number of equation you will get here in optimization will be 5. Okay, if it is 1, then you will get 1. If it is 2, you will get 2. Okay, so this is called a unconstrained. Okay, so suppose we wish to minimize a cost function subject to some equality and inequality constraint. Okay, if you are considering equality and inequality constraint, you know what is equality constraint and what is inequality constraint. So now if this constraint are specified, okay, if somebody says that equality constraint is this much and inequality constraint is this much, and if it is specified in your problem, then method which you will try to use by this minimize j equal to u and then obtaining solution by setting the partial derivative of this minimize will not work. Okay, so if it mentioned earlier one, we have not considered equality and inequality constraint because the solution obtained from the procedure may not satisfy the constraint. So if you just use this method, unconstrained system method, and then solve it, so you will not get the required answer because we have not considered this constraint equality and inequality constraint. So what you have to do is, so therefore an alternative method is required in order to take a constraint into account. So that normally when you do an optimization, you will not go for this type of method because in optimization we have to see all types of constraint like equality constraint, inequality constraint. So then alternative method we have to consider that. Okay, so that alternative methods. So we will try to solve it one example. Okay, so now first let us consider that case only it has a equality constraint. So just now let's forget about the inequality constraint. Let us consider in a optimization problem there is only equality constraint. So now what you have to do is we have to minimize. Okay, so why we are doing minimize? We want to make cost as far as cheap, right? As far as possible cheap, right? So this j x of u, minimize this j x of u, but when you minimize, it has to subject to g x of u. So what g x of u? It is a equality constraint, right? But this is a cost function which we are trying to minimize. But when you minimize this, it has to fulfill gx comma u, that is equality constraint. What is x and u? You know, right? Already we have learned in lecture 3 or 4 this all, right? So now in such case, if you are required to do optimization considering this equality constraint, so in such case the procedure is to form the composite cost function. So now if you are required to do minimize this considering an equality constraint, what you have to do is, so you have to form a composite cost function. Okay, composite cost function which will involve c equal to, actually this c is a composite cost function, so it will be equal to jx comma u because we are minimizing this, but it has to fulfill the equality constraint. So now we have to form the composite cost function like this. Okay, so this c equal to jx comma u because we are minimizing this, and then minus lambda dash x gx comma u. This gx comma u is a equality constant. Okay, we have to fulfill that. But in optimization, so what you have to do is you have to form one composite cost function. So composite cost function C, how you will find is you have to minimize that function j minus 1. Here I will consider is a constant, and then it has to be fulfilling the equality constant that gx comma u. Okay, what is j? Okay, so with that j, it is a raw vector of a variable, and it is called a Lagrange multiplier. Okay, so in mathematics you might have learned what is meant by this Lagrange multiplier. Okay, so now here if you consider the equality constraint, and if you're required to do a optimization, how you will do is, so you have to form a composite function. So don't worry about these two. These two will be given in your question or in your problem. It says you have to minimize this, and it has to fulfill this one, means equality constant. So now how to solve that means we have to solve by forming one composite function. How you will form a composite function is C is a composite function, cost function, which will be equal to minimize that function jx comma u. So this is a standard how we can form the composite cost function minus lambda dash. Some use lambda dash, some keep as lambda only. It's fine, whatever it may be, lambda dash into gx comma u. Okay, where this lambda dash is a Lagrange multiplier. Okay, so this is how we have to form the composite cost function to carry out the optimization considering the equality constraint. And this number of this multiplier, Lagrange multiplier, is equal to the number of equality constraint. So this g of x equal to 0 is equality constant. If there are two equality constant, multiplier will also be 2. If it is 1, it will be 1. Okay, so this composite cost function is minimized by treating the Lagrange multiplier as an additional variable. So that's why we have created one additional variable here to form a composite cost function. Then after that, what you have to do is you have to solve this equation or composite cost function. Then solution of this, when you solve this, you will get one solution. So that solution is a minimum solution which satisfies the equality constraint. Okay, so if you get this answer or a solution, then this solution will be the minimum solution which will satisfy the equality constraint. Okay, this is how we can carry out the optimization considering equality constraint. Okay, so now earlier one we have solved example. So that is this is a step, and then now here we try to solve. In earlier when I solved this problem, I said that there is a mathematical procedure how to solve. Earlier one is like a hit and trial case. We have solved this, right? Cost. But let us take same example which we have considered earlier. Okay, considering two generator. Okay, but now here we will consider it has to fulfill the equality constraint. Okay, and then carry out the optimization. So earlier I said that it is just a hit and trial and error method, but here we are doing a numerical method. Okay, so now let's consider a two generator with the following cost function C1 50 into P1 plus 3 into P1 square, which we have considered example in earlier, and then C2 given by this equation. So now let's us assume that here also G1 and G2 generator do not have a maximum limit. Why we are considering there is it does not have a maximum limit is because we have not considered the inequality constant. We are considering only equality constant. If there is inequality constant, so there will be minimum and maximum. So that's why here we are considering only equality constant, and then let's try to carry out the optimization. And then what it has to do is question is says find the least cost schedule if a demand of 550 megawatt is to be made. It's same like earlier problem. We have to make 550 megawatt at the same time. Okay, so it does not have a maximum limit, which means inequality constraint is absent, but we are considering only equality constraint. So now how you can do is here same earlier step we have explained. So total cost is given by, generally total cost will be given by C1 plus C2. This is which is to be minimized, right? This C1 plus C2, actually it is like a J x comma U. Okay, this C1 plus C2 is a J x comma U is a total cost SMS, but this has to be minimized subject to, it has to fulfill that this generator 1 and 2 power should be equal to 550 megawatt, or P1 plus P2 minus 550 equal to 0. So subject means this is a equality constraint, 1 plus P1 plus P2 should be equal to 550, because generation from P1 and P2, it has to meet this total demand. Okay, so this has become as a equality constraint. This is a constraint. So now total cost C1 plus C2. C1 is given here in the question. C2 is also given in the problem. It has to be minimized, but subjected to, when you minimize, it should not be, okay, it should fulfill 550 megawatt, total demand of 550 megawatt, means P1 plus P2 minus 550 equal to 0. So therefore, considering the equality constraint, how you can do is, you have to form a composite cost function, right? Composite cost function C will be equal to C1 plus C2 minus, here I have used only lambda, it's okay, Lagrange multiplier lambda into P1 plus P2 minus 550. So same like earlier, that step I have given C equal to, what it has given is J x comma U minus lambda dash of G comma G of multiply, okay, so sorry, lambda into lambda dash into, okay, so lambda dash into G of x comma U. Same. So here J of x comma U is our total cost function, which has to be minimized, and then it has to fulfill the equality constraint Gx comma U is this one. But here when you carry out the optimization, there is a standard in this step, it has been given, it has to be multiplied by Lagrange multiply lambda dash, but here I have given lambda, okay, and then minus, this minus, it has been the standard to carry out the optimization considering the equality constraint. Okay, so this is how we have to form. This is a condition given, then from this condition we have to make that, okay, so cost function, and then equality constraint we have to frame that, because here it has been given cost in the problem clearly, it has to meet the total demand of a load of 550 megawatts. So which means P1 plus P2 equal to 550. Then to carry out the optimization, we have to form a composite cost function, which is equal to C, and it will be given by this cost minus Lagrange multiply lambda into P1 plus P2 minus 550. Okay. Then what you have to do is, other thing you try to read that, you will understand that. But here this P1 and P2 can be a control variable, right? We can adjust power generation on P1 and then P2, not the lambda, right? So P1 and P2 are control variable, and there are no auxiliary variable as such as of now, because P1 and P2 is a control variable, and we don't have 550 will be a fixed one, and C1 already it has been given in terms of P1 and P2. So P1 and P2 are the control variable, and 550 will be constant, but we don't have any other auxiliary variable X. That auxiliary variable we used to consider voltage, power factor, and then all, right? So in here we are not bother about this one. So just to make things simple, okay, so we are considering based on this equation, just P1 and P2 are control variable are there, no auxiliary. So now in such case, how to solve this? Now differentiate with respect to control variable. So here control variable is P1 and P2, and auxiliary, there are none in this example, right, just now, and then lambda, and equating all derivative to 0 we obtain. So now what you have to do is, after forming the composite cost function to carry out the optimization, you have to differentiate, okay, with reference to control, okay, which means your cost function has to be differentiated with respect to control variable and the auxiliary variable if there, but in this example we don't have auxiliary variable, and then lambda and equate to 0, so then we will obtain. So now this cost function you differentiate with respect to dc by dp1. Okay, first cost variable. So now how you will get is, so here p1. Okay, so first, so you are getting 50, right? When you differentiate, plus 6 into p1, so minus what you will get, p1. Okay, means lambda only. P2 will be treated as 0 because we are differentiating with respect to p1. So for whatever cost involved in the p2 will be 0 because this p2 will be treated as a constant since we are carrying out the derivative with respect to, or differentiation with respect to p1. So then first equation you will get this equal to 0. So we are, all the derivative we have to equate to 0. Then similarly dc, and then we differentiate cost function with respect to p2, so then you will get 50 into 5 p2 minus lambda equal to 0, and p1 will be treated as a constant here. Then next same cost function we have to differentiate with respect to Lagrange multiplier, that is lambda. So when you multiply, differentiate with respect to lambda, then you will get this. Okay, so p1 plus p2. Okay, so minus p1 plus p2 minus 550 will be equal to 0. So now if you make in the form of matrix, so you can make like this, right? Okay, so here optimization means we'll make in the form of matrix and then we'll try to solve that. Okay, so now when you make in the form of matrix, so now we can make arrange such a way that p1, p2 and lambda. So now if you multiply that, you will get this one. Okay, 6p1, okay, minus lambda will be equal to, you have to take it at the right hand side, so you'll get minus 50. And then similarly second one, 5, so p1 is 0, so 5 minus 1 equal to p2. Similarly you will get that. Then here lambda you'll get 1 1, and here I have kept positive. Okay, if you want here minus, then it will also be minus. Okay, so you are getting this type of equation. So now basically what we are doing is, so we are differentiating with this control variable and then auxiliary variable and then Lagrange multiplier and equating to 0, and then finally we are trying to find the solution. So now how to solve? So if you get this type of matrix, so you have learned in the mathematics, you will be able to solve. Okay, so by how you will be able to solve and get the value of p1, get the value of p2, and then get the value of lambda, right? So you will be able to solve that. So how you will solve that is, so there are, first we can see there are 3 independent equation you will get. Okay, so this equation, and then another equation. So which means there are 3 independent equation in the 3 variables can be solved by, so pre-multiplying the column vector on the right hand side by inverse of the matrix on the left hand side. So here I have not solved this one. Okay, so because in the mathematics you have learned, okay, so how to solve such type of matrix equation. So if you are able to solve this matrix equation, then you will get how much power has to be generated from the generator 1 and generator 2, so that your total demand 550 can be met, and then what is the cost of energy per hour it will come, that will be given by that constant. Okay, so here I have not solved, so please try to solve and see that. See if you solve that by using this matrix method. Okay, if you have forgotten, you take this matrix and ask to the math teacher, so math lecturer, so he will solve that. Okay, so if you solve that, then you will get p1 equal to 250 megawatt and p2 equal to 550 megawatt to fulfill our total demand of 550 megawatt. Okay, so P1 has to generate 250 and P2 has to generate 300 megawatt to meet the total demand of 550 megawatt. And then as far as our, based on our optimization, cost you will get is Newton 1550 per megawatt hour is will be the solution for all this. Okay, so this is how we can carry it out, just considering equality constraint only. Okay, so this other thing here, you read this, all you will understand this. Okay, so just condition it has been given, but very important thing is you should be able to get this. Okay, so by solving that matrix, how already step has been given, only left is, so I have not solved for matrix. So, but to some extent I have given hint on also by pre-multiplying the column vector on the RHS by the inverse of the matrix on the LHS. So you will get P1 will be equal. So that's why I have given verify that P1, whether you are getting P1 equal to 250 megawatt, P2 equal to 300 megawatt. So total demand will be 550 megawatt, which means we are fulfilling the equality constraint. And then when it fulfill the equality constraint and the total load demand, so cost is coming out to be this much. Okay, just now don't worry about the cost. You may think that 1550 per megawatt hour is very high, but just now, just for a simple understanding purpose, we are carrying out. Others, you try to see that. So that's about the equality constraint optimization. So now normally, so there will be a certain inequality constraint, right? Always you will not get an equality constraint. So what happened wherever is a constraint by inequality constraint, which means maximum power can be generated, power in the generator one can be generated there, right? And then minimum power can also be there. Here in equality constraint, we are not considering any input, just we are considering the rating of the machine. So P1 will power one will generate this much, two will generate this much, but we have to see other constant like inflow to the turbine. So whether you will get enough inflow to generate this set amount. So now this will become an inequality, which means maximum minimum. So just I will take one practical example. Hydropower, so it might be written 84 megawatt machine or 60 megawatt or 15 megawatt, example in Kurichu 15 megawatt, but we are not generating 15 megawatt throughout the year. Sometime it will be below 15, sometime it may be generating around 16 17 megawatt also. In summer there are enough inflow we are generating. So this we have to consider a inequality constraint. So if you consider an inequality constraint, whatever we have solved earlier will be a wrong now. Okay, so which means we have not considered the inequality constraint. So now if you consider an inequality constraint, then what it will happen is an inequality constraint usually arises when one wants to place some limits on the value of the variable. Okay, so for example, power output of generator is limited by its capacity, right? It will have its own capacity, right? And then a simple and approximate way of ensuring that limit are not hit, that is inequality constraint are not violated. So now when you do a optimization, cost optimization, you have to be mindful that that inequality constraint also should not be violated. Okay, to argument the composite cost function discussed earlier. So the cost become extremely high if limit is violated. So now if that inequality limit constraint limit is violated, then cost will become very, very high, which will not be able to afford by our customers. So then we have to carry out the cost optimization considering the inequality constraint. So now how we'll do is, so now you know that when you carried out the optimization with inequality constraint, so this one you know what is minimize this function subjected to this is equality constraint. Okay, when you carried out the inequality constraint, it will fulfill the equality constraint. At the same time, extra it will be fulfilled is inequality constraint. So this one is general representation how we can carry out the optimization with inequality constraint. Okay, so in inequality constraint, we will consider equality constraint as well as inequality constraint. So inequality constraint is given by, it will have a certain minimum and maximum value, right? So this can be rewritten, that inequality constraint or this last equation can be rewritten at h x of comma u can be written by this portion also, or we can write minus h of x is equal to minus h minimum, right? So this one can also be rewritten, and then this equation can be generally we can rewritten as a inequality constant. So if you use this one, it's find very difficult to solve. We will rearrange this for our convenience, and then we will rewrite this inequality equation as q of x comma u will be less than or greater equal to q max. Okay, so now onwards, so earlier we have said that h min minus is inequality constant. So we will, for our convenient purpose for solving the problem, So we will try to rearrange this, and then we'll write this as a inequality constraint. Okay, so other method, so method to solve will remain same only, but here what you have to do is we have to consider the inequality constraint. Okay, so now let's see what we can do is, so now procedure for minimizing the j subject to the constraint is to form a composite or argumented cost function as follows. Okay, so same. So you will try to find, but here extra you will get is, actually this one is equality constraint. So earlier example we have solved till here only, but now we are considering inequality constraints. Extra you will find is inequality constraint, and then we have to define that inequality constraint, how much, and then we have to find the function p of t, such that it is very small. It should be chosen very small, and if t is very less than 0, and otherwise it is very large. Okay, we have to choose this, and then a penalty function also we will introduce, that p of t will be equal to e to the power beta t, where beta will be greater than 0 and is suitable for this purpose, which means how to choose the value of beta. So normally its condition is greater than 0. So now here also there are certain limitations. When you choose the value of beta, what you have to do is you have to choose randomly. Okay, so we'll see that this is a procedure to carry out the optimization considering inequality constraint. So now same like previous example only, we'll consider the, okay, so same like previous example, we'll consider the same example. So consider the two generator having cost function c given by these two. Okay, and then here what we have to do is we are considering the inequality constraint, which means this two generator g1 and g2 have a maximum limit. So which means p1 can generate less than or at the max 290 megawatt, and then p2 also made a 290 megawatt. Okay, means it has a certain maximum limit. Now if such case, find the least cost schedule if a load demand of 550 is to be met. So how to find the cost? Okay, least cost. So now in such case, so now you can see this condition clearly. The solution without inequality constraint is not feasible, since in our equality constraint we have found out that P2 is 300 megawatt. It has to generate 300 megawatt to meet a 550. So now our in this example, it has made the maximum limit is almost 290 megawatt. Means it is violating the one constraint. So if it violate the one constraint, what it happen? So it cost will shoot up, right, very high. So now in this condition they have make a restriction. Okay, generator 1 capability is 290 megawatt, generator 2 also 290 megawatt, but when we consider the equality constraint, generator P2 has to generate 300 megawatt to fulfill the 550 megawatt load. So it violates the constraint, right? P1 it is fine within the constraint, but P2 it has been violating. It has to generate 300 megawatt, but its maximum capacity it has been given is 290 megawatt. So in such case, how to solve? Okay, so the correct solution can be obtained by following the procedure outlined below. Means you can just guess what will be the answer, but okay, so following procedure can be adapted. So similarly, like equality constraint only, first what you have to do is total cost has to is given by C1 plus C2, and then this has to be minimized. Okay, actually this C1 C2 is a J, right, in earlier just a general format, so which is to be minimized, but when you minimize it has to subject to fulfill P1 plus P2 minus 550 equal to 0. This is a equality constraint, right? We have to fulfill that, but at the same time P1 should generate around 290 megawatt. P2 also should generate around 290 megawatt. Means it is not saying you have to generate this much, but what it's saying is maximum P1 can generate is 290 megawatt and P2 can generate 290 megawatt. So which will become as an inequality constraint. So in such case, so process will remain same like the equality constraint, but here we have to form a argumented cost function considering the equality as well as inequality constraint. Okay, so which will be equal to this cost function will be equal to C equal to C1 plus C2, and then till here we are considering for equality constraint. Okay, C1 plus C2 minus lambda into P1 plus P2 minus 550. So why this is a equality constraint? We have to fulfill when you minimize this cost, then we have to fulfill P1 plus P2 minus 550. It's a equality constraint. But here again another constraint they have made is P1 should generate 290 megawatt. P2 also within maximum limit it can generate is 290 megawatt. So then what we have to do is we have to add up or argument in the cost function for equality with this P, what is P into small p into P1 minus 290, because it has been made that it should maximum is 290. So P1 minus, then for P2 also minus 290. So this will become a cost function. And then what we have to introduce is in inequality optimization, what we have to introduce is we have to introduce a one penalty function P of t, and then in general step, I have explained that penalty function will be given by e to the power beta t. And then how to choose beta, we have said, right? So that beta value should be greater than 0. So now here, for simplicity, you can choose 1, 2, 3 like this. But we will try to choose 3 and then see how it will go. Okay. So actually, it is like a trial and error method how we will choose the value of beta. So, but it should not be less than 0, which means minus 1, minus 2 should not be there, but it should be greater than 0. You can go up to 100 also, 100 and above also. Okay, so but here we'll try to choose 3 and then see how it. So now minimum value of C is obtained by calculating the derivative with respect to variable P1, P2 and lambda. So similar case here, I have not formed a mathematical equation. So now what you have to do is this cost function, you have to derive dc p by dp1 like this. You have to make an one equation. Okay, then similarly you have to do dcp dc by dcp2 and then lambda, and then you will get a equation. So when you get a equation, so here p is e to the power beta, right? Beta t. So you have to substitute that and then differentiate. And then what you will get is, so then you will get this as a result will obtain the following nonlinear equation. So we have to form in the form of matrix equation. You try to solve this. Differentiate with respect to P1 first, then differentiate with respect to P2, then differentiate with respect to lambda, that is Lagrange multiplier, and then see whether you are getting this or not. So you make this in the matrix form, and then you have to solve this. Okay, so how to solve this? So you might have learned in the power system stability analysis. Okay, so if you get this type of problem, how to solve. Okay, so if you solve this and then you have to get the solution, how much P1 and P2. So now this equation normally involve e to the power beta, and then also it will not be a linear. So it will be a non-linear and cannot be solved by direct matrix inversion. So in equality constraint, we get done that direct matrix inversion, but here you cannot do a direct matrix inversion. So in such circumstances, one can try to employ a numerical techniques like Gauss-Seidel or Newton-Raphson method, which you have learned in the power system stability and analysis. Okay, you try to solve that. Okay, using this Newton-Raphson method or Gauss-Seidel, whichever you find easy, both way will work now. Okay, or alternatively, we can also use that gradient descent method. Okay, you try to solve by this Gauss-Seidel and Newton-Raphson method and then see them. Okay, so or you can do this gradient descent method in which the LHS side of the above equation is evaluated at guess value. Again, here you are guessing. Okay, so P1 has to be 250. Just say, and P2 also 250, so that it will come how much? Okay, 500, and lambda should be this. Just you guess and keep on solving that, but it will consume a lot of time. Okay, so what you can do is you use that Gauss-Seidel and then method. Okay, so now here I have just seen using a gradient descent method, and then we have tried to solve this. Okay, so now what you can do is note that LHS is a gradient of cost function. So that's why I will write del inverse of this into k cost function will be equal to, but what we have to do is we are guessing p1 equal to 250. First case is 250, p2 also 250, and lambda we have kept 1550. So p1 k, p2 k, del, okay, lambda k plus 3, wherever p is there, we'll try to keep on guessing now. So now when you guess, and then again now from here itself you will know that 250 plus 250 is 500, but our total demand is 550. So again you will not fulfill, then you try to change this p1 to 300. It cannot go 300 because your maximum limit is 290 capability. So you have to guess, keep on guessing, then you change that p1. Okay, k value can be 1, 2, 3, and then so on. Okay, so you try to change that, and then if you solve this, then you will get this. Okay, so this type of equation. Okay, so which means the trick is to change p1, p2, and lambda in the direction which is negative to gradient direction. So keep on this, and then you will try to change this, and then you will get the certain value. Okay, one keeps updating this value. Second time you will keep on changing now. So 2 times, okay, 1 plus 1, 2, or 0, k will be equal to 0. So 0 plus 1, then k value will become 1, 1 plus 1, 2, and then so on. Okay, so you keep on updating value of p1 and lambda in this fashion, descending till there is a very little difference between the values of variable for 2 consecutive iterations. So if you keep on changing, then your value should be very difference between two variables should be very small for a 2 consecutive iteration. So if that is the case, then we can say that that is a solution. So now it find very difficult for you all so to carry it out. You might have forgotten the Newton-Raphson method, Gauss-Seidel method. So just simplicity. So I have developed simple MATLAB program which implement, okay, so you can copy this program and run it in the MATLAB, and let's see. Okay, just copy this and then you try to run in the MATLAB and then see at what value of x, okay, does it converge to. When you keep on changing, when it is converging means your difference is becoming minimum, and do the generator power remain within the limit specified. So now here x I have written 250 and then what. Okay, this one we have make a guessing, right? So now when you see that, then you have to see that whether first one is we are fulfilling that 550 megawatt or not. Then we have to see that whether generator okay power remain within the specified limit or not. Just now it is within the specified limit, but we never know it will fulfill 550 megawatt or not. If not, why? Then what you can see is now you try to change that x, then what is the effect of varying the value of a and b. Okay, so keep on changing this value, and then you try to see what if beta is chosen to be 2 is small, so you try to see 0.1, and then 2 high 1000 you try to see, and what answer you are getting. Okay, so please try to see that. So this is how we can carry out the optimization considering inequality. So now if you get puzzled with this gradient method, so now you are introduced to this Gauss-Seidel and Newton-Raphson method. So I have given the basic equation. It has been framed, basic equation has been framed. So you try to solve using Gauss-Seidel and Newton-Raphson method, any one method, and then try to see how much it can. Okay, when you solve that, it should not violate the any constraint, either equality or inequality constraint. If any one of the constraint violated, then cost will be very exceptionally high. Okay, which all the customer will not be able to bear this. Okay, so that's all for today's session, and if you have any doubt, so let me know. But so I have planned only this much for today, and then tomorrow there is fest test, and then we have decided that I will call off the class. Okay, so thank you for coming online.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.